only a certain amount you want, really. But yeah, no. So a coronal mass ejection is this massive outburst of plasma, which is just essentially ionized matter. So we're talking about atoms, molecules that have been stripped of their electrons, yeah, they've broken free from the sun's magnetic field, and if you're unlucky and they're pointed toward Earth, those charged particles can come your way.
My favorite thing about that is that it's like a Russian roulette game, because
Right.
the whole plasma ball is like polarized with charge, and if the polarization lines up opposite of the Earth's magnetic field, it'll get sucked down the magnetic field lines and cause all the crazy aurora and everything that you'll see. But if
Very
it's
beautiful.
anti-aligned, it'll just get reflected into space and repelled basically. And so whenever you see, like, it's especially like if you're seeing this huge like chunk of explosion coming at you, and it's like there's a 50-50 shot about whether this will be the one. And
Yeah, well, that's right. Well, it's funny you say that, because that's one of the big problems is you don't see it coming, because it's what we call optically thin. You don't actually see it. You know, you can detect it as it leaves the sun, and as you rightly said, you see the impact on Earth's magnetic field with the aurorae, but you don't. Through telescopes, you don't see it coming. So that's the big problem with it, actually.
you know, if we could see it coming, you just know there'd be like sports betting, but for this,
That's right.
with odds updating as it approaches.
That's right. Which continent gets the worst impact, or
Exactly.
who has the nice aurora? The southern hemisphere, the northern hemisphere,
You could do
Finland, Iceland.
combination bets where it's like how far down the latitude goes, plus like how many transformers blow.
Yeah, right. Yeah. How many satellites around the Earth get shorted out, that kind of thing.
Exactly. So, are we seeing more of these than usual? I feel like I've seen more news about this lately.
Well, I think you know this, Joseph. It's near solar max this year, and by solar max we mean the sun is really active. As you know, has a 22-year activity cycle, and we just happen to be right at the top of the activity cycle. So yeah, we should be seeing more of these. It's actually a really natural consequence of that cycle.
It's so fascinating. The sun goes through phases, just like everything else in the universe.
I'd say everything in the universe has cycles, periods. It's sort of that old adage that everything in the universe rotates unless you stop it doing so. Like, a pencil on a desk is being stopped from rotating, but everything rotates. Everything has a period, and the sun is no different. This 22-year period is based on its magnetic field, of course, but that's ultimately related to the rotation, the internal rotation, the differential rotation inside the sun. Really, really very interesting.
The 22 period is a really critical point there. So a 22-year period basically means it'll go from maximum to maximum again over 20, about 2 decades,
Correct.
right?
That's right. That's right. The half period's 11. That's right.
So that's so funny to me, because all the articles that we're talking about the coronal mass ejection that happened a few days ago were saying stuff like it's the largest that has been observed since 2017. And that sounds pretty wild. But if you think about it, 2017 was right around the solar minimum. So it's like saying that the flare that occurred at the solar maximum is the largest it's been since the time the flares weren't so big. And it's like,
It's sort of
that's
obvious.
substantially less punchy.
Yeah, that's right. Yeah, no, that's right. It's like this is a really big iceberg because it's bigger than any we've seen since the last big one. Yeah,
Yeah,
it's silly.
exactly.
Yeah, it's a bit sensationalist, which of course a lot of science writing is these days.
Right.
But yeah, no, it's completely natural. It's happened as long as we've been observing these activity cycles on the sun, which really is sort of back to the days of Galileo when he first saw the first sunspots, of course. And sunspots are a natural manifestation of the magnetic field lines threading the surface of the sun. So these things are not sort of new. It hasn't just come around the corner in the last 20 years. We've known about these things for 250 years.
Yeah, Galileo didn't use his telescope to look at the sun, right?
Yeah, well, he must have actually, because it's very hard to have figured out how he would have seen the sunspots otherwise.
Maybe like
Because he
what about something like what do they call it? Like camera obscura, or like a pinhole projector or something like that?
Yeah, that's possible. I'm just thinking about that. I'm actually not sure of the history of that, but also one can see the sun. It's very, very low on the horizon, and certainly if it's musk, if there's dust in the air, or it's a murky atmosphere, you can see the sun in a really deep orange or really deep red. One could imagine being able to look through it. And don't forget, Galileo's telescope was maybe an inch or two across. The lens was tiny. And don't forget, he ultimately went near blind toward the end of his life. So he did suffer for his observations.
That would explain it, actually.
Oh yeah, he was
You know,
everything you
that
tell
does
school kids.
that does make sense that, so during the last partial solar eclipse, there was an annular solar eclipse, but in where I'm living, it was a partial one, a pretty large partial one. I was taking pictures, and for the first bit where the sky was clear, I definitely had to use I took eclipse glasses and I taped them to my phone, and it worked well enough. But as the clouds started rolling in, I noticed that I could just get a picture without needing the eclipse glasses because the clouds were obscuring it. And I at one point I accidentally, when I was looking up to see where to put my phone, I accidentally glanced at the sun. And even though I looked away immediately, I registered that I saw the partial eclipse with my eye through the clouds, and I just thought that was the coolest thing. It's very unnerving.
It is cool, and I'm so glad you had the experience, but it should be avoided if possible, because as you know, the sun can damage human eyes very easily.
Oh yeah, oh yeah. No, this was super accidental glance.
Yeah.
I not like a point like, look at the solar eclipse.
Well, it's one of those things where I've done a lot of work in taking astronomy to school kids across many countries, as it turns out. But it's one of the first things you always say is never ever look at the sun directly, because it doesn't take long to go blind. Actually, it's sort of 8 to 10 seconds and you're in big trouble.
It's kind of horrifying, actually.
Yeah, well, I mean, it has been done by people in history, and they of course suffered, unfortunately, the consequences of having gone blind. And the human eye is just not well adapted for that level of intensity.
Ironically, though, it's perfectly adapted for the sun, but not staring directly at it.
Yeah, right, not staring at it. Yeah. But it sort of gives you a nice contrast for astronomical objects, because, of course, you can stare at the full moon and your eyes aren't damaged. So it gives you a sense of how very much brighter the sun must be that our eyes can do that.
So that's right? You can stare at the full moon and your eyes won't be damaged. But to be honest, when I'm looking at the moon through my telescope, I feel like my retinas have been nuked, and it just torpedoes my night vision.
Yeah, of course, completely. Yeah. Well, don't forget to tell I can't remember how large is your telescope? Is it 8 inches diameter?
It's a 6-inch, yeah.
A 6-inch diameter. So that's collecting an awful lot of light, right? I mean, I can't remember what the average human pupil is, but that's.
I know this one. It's
like 8 millimeters, is it?
It's like a order of like a centimeter to a centimeter and a half, I think, when fully open.
A center. So that means your telescope is 15 times the diameter of a human eye. So you're collecting an awful lot of flux. You're collecting 15 times more photons. So your poor eye is probably thinking, "Don't show me the full moon."
That makes complete sense. So circling back to the sun bit. So I did a little bit of research, and because I found the comparison to the solar minimum absurd. I did a little bit of research, and it is the largest solar flare since the last largest solar flare during this last solar maximum, about 2003, which lines up with that 22-year cycle. And so that was an X-class flare, an X45 class flare, and it was actually the most powerful solar flare ever measured. And I thought that was really interesting because I've heard of more damaging solar flares throughout that have been recorded. Like there was one in the late 1800s that I don't know if they knew it was a solar flare at the time, but I think they recorded extra large sunspots, and then a couple days later all the telegraphs in the world were like broken and like there was like the capacitance of the air had like quadrupled or something like that. But I think we have an estimate of that one. So do you think that this was a very powerful solar flare, but maybe wasn't aligned with the Earth's poles, and that's why we didn't see as much of an effect back in 2003? Or
yeah, that's possible, of course. Or it could just not have been directly pointed at the Earth. We could have been sideswiped, where maybe the one that you're referring to in the 18th century or 19th century was directly pointed at us. And so
that's a really good point.
Yeah, so I mean, I think that's a really big misconception, is if you have the sun here and you have these enormous explosions of material in these coronal mass ejections, if the Earth is sort of in its orbit, sort of roughly over here, the beam of particles could actually, the solar wind could actually pass sort of underneath, quote unquote, the Earth and not impact us at all. So it depends where the solar flare is, it's sort of exploding toward. Like if the vector is not co-aligned with the Earth's orbit, and don't forget, the timing has to be right. because of course, let's say you know, the Earth as it's orbiting is sort of doing this. If the timing isn't right, it can either pass behind or in front of the Earth's orbit, so you're not directly impacted either. So the direction and the timing has to be right for us to be fully impacted.
That's really fascinating. So, like, will the sun get better with practice?
It's a terrible joke. That was pretty good. That was pretty good. There you go. That was good. I like that. Yeah. I mean, you have to remember, though, that don't forget, though, the sun is really old. It's 4.5 billion years old. If you compare it to really young stars, let's say the stars in the Pleiades, the Seven Sisters, for instance, those are 120 million years old. Those are really active, and that's because they're spinning really, really quickly, which winds up the magnetic field. So those types of stars, these very, very young stars, they have very, very much more active flares. And so if we were orbiting one of those types of stars, a very young star, at the same distance we are right now from our sun, we'd be in big, big trouble. We'd be blasted by X-rays and UV and particles and so on. And I don't think our magnetic field or our ozone layer would be able to protect us, actually.
Interesting. That's really, really interesting. So is it the orbit, or is it also something to do with the sun's like level of activity?
Yeah, the sun is really very, very inactive. I think at any given time, even during solar maximum, the sun's surface is covered by about 0.5% by area with these sunspots, which are magnetic fields sort of poking through the surface. So that's at the maximum 0.5%. So even though you see sunspot groups and you think, oh, that's amazing, that's super cool, look at how active the sun is, as a fraction of the total surface area of the sun, it's really a very, very small amount. In these super young stars I was talking about, you can get sunspot filling factors or star spot filling factors of about 30–40%.
Wow.
So that's enormous. Their magnetic field is very, very much more active. It's incredible.
That's so cool. 40%. So that's like half of a sunspot, basically.
That's like half the surface, yeah. And if you go down to some of these M stars, these M-class stars, our sun's a G-type star. These M-class stars, which are very, very low mass stars, some of their surfaces can be near 100% star spots.
Oh my God.
It's incredible. Yeah, so they're just incredibly magnetically active.
So, this is more personally related to like a personal interest for me because it's related to my research. But with these stars, where you have like 50% of their surface, being sunspots, does that affect stuff like the stellar wind? Like how far they're so for viewers that don't know, the stellar wind is basically as a result of a star's magnetic field carrying charged particles away from the star and depositing it into the area around the star. So if the sunspots are some level correlated with the star's magnetic field, if you have these stars that have a very big sunspot filling fraction, does that mean you'll have like one side of the star that has a weak stellar wind versus the other?
Well, so that's a really interesting question, and it's not quite as simple to answer as you think, actually. So don't forget, a stellar wind, or for us, a solar wind, those particles have to be, they emanate from open field lines, magnetic field lines, which means if you think of the star as an orange on my hand, right, the field lines have to be open so the particles can flow along them. When a star is very, very magnetically active, what you actually get is these loops, these magnetic loops that are called arcades. And unless there's a coronal mass ejection where the magnetic field blows open, the particles actually do not escape. So the solar wind or stellar wind is a very sensitive function of whether you get coronal mass ejections or not. If you don't, the wind doesn't increase that much because the particles cannot escape the magnetic field lines.
That's incredibly interesting.
Yeah. So for instance, in our sun, where let's say, again, my fist is the sun, let's do it that way. If this is the North Pole and this is the South Pole, the field lines, well, I can't really do it easily here, but the field lines are really, really big and open like this. But what happens is if you've got these open field lines, the particles can escape. So the greatest part of the solar wind actually escapes through the magnetic poles because it can go along these open field lines off into solar system space.
That's so cool.
Yeah, so your question was a really good one, but not that easy to answer, actually. There's some complexities in there.
It always ends up that way.
Yeah, of course. Stars are complex beasts after all.
I have a 40-page book by Chandra Sekhar that suggests otherwise.
Well, unfortunately, at least unfortunately for me and you, he was a genius, right? So Yeah, he knew stars inside out.
So before we move on to the next topic, actually, I can pull up a cool picture of the flare that that
Oh
eventually
yeah,
hit the
show us,
Earth.
show us.
So this is a picture from the NOAA Space Weather Prediction Center, which in my opinion is like one of the coolest websites on the internet, where you can just watch the sun live, and they're like, "Oh, some space weather coming up." So this is a picture of the sun. It's at 131 angstroms. I've always wondered this. This is the filter they pick. Is the flare just not visible in all filters? It's such a big event. You'd think it'd be visible in all filters, but like,
So that's a really good question. I think the answer is, if your eyes could do it, then yes. We don't have good enough observatory spacecraft to observe it in all filters. Now we can observe it in the wavelength that our eyes can see, human eyes can see, but 131 angstroms is sort of extreme ultraviolet, or just bordering on what we call soft X-rays, very low energy X-rays. And don't forget, our eyes can't see in that domain, which is why we need the spacecraft.
right.
So this is a very interesting one. This does look like a flare, a flare event, which is this really big release of energy. If it's in extreme ultraviolet or soft X-rays, that is definitely accompanying a large magnetic field, and the plasma gets accelerated along the magnetic field lines and releases all this energy. But if we were looking at the sun at that point, if our eyes could see something so bright, I'm not sure what we would see. We may be able to see something, because what ends up happening is if you've got a magnetic field line like this on the surface of the sun, and the plasma ends up going along the field line and being accelerated and releasing this, extreme ultraviolet and soft X-rays, you do end up seeing it, but you're not seeing it itself. You're seeing scattered sunlight from the surface of the sun off the plasma into our eyes. So you might be able to see it in the optical, which is where our eyes see, of course, but you're not seeing it directly. You're seeing scattered light from the surface of the sun.
Okay, that's a really important subtlety, which I feel like is often glossed over in discussions of this.
Yeah, that's right. It is very, very subtle. People think you're seeing the direct optical light from the flare, but typically, if you're seeing a flare, you get radio emission, because of course the electrons are spinning around a magnetic field, so you get lots and lots of synchrotron radiation, and then you get they're being massively accelerated, because these magnetic fields are enormously strong. So what they do is they accelerate the particles, and of course, accelerating charge in the magnetic field releases energy. So you get this massive release of high energy, extreme ultraviolet X-rays and so on. But the visible light that you tend to see from flares is reflected sunlight. And you can tell this because when you look with a special instrument called a polarimeter, the light is polarized, which means it's being scattered. And that's how we can tell.
That's so cool.
Yeah, it's amazing.
If
you're I apologize. Yeah, if you're interested in why I seem to be really into this, is my PhD was actually in this type of science, and so the things you're describing was exactly what I used to do in the mid-90s.
So count yourself lucky, guys. David is literally one of very few world experts on this stuff.
Yeah, well, I moved away from it a little bit, but I still remember all this stuff from my thesis, and of course, I was referring to the Pleiades, these very young group of stars. They're a big